time for our first session of the second day. I'm Professor Michael Duke, and I'm going to be your chair, conference chair. And we have a series of some wonderful speakers in our session, which is titled Resource Recovery from Wastes. And it's my greatest pleasure to introduce our first speaker, Dr. Qian Fu. Dr. Qian Fu is an ARC Future Fellow and Senior Lecturer at the University of Technology, Sydney, so here, and is currently leading a research group in the Centre for Technology in Water and Wastewater. Now, I think I'll stop there because I'm sure your presentation is going to do wonderful justice, better than my introduction. So please join me to welcome Dr. Fu to give his talk on cost-effective water production as our keynote speaker. Thank you very much.
Thanks, Michael, for the introduction. Good morning, everyone. I'm Qian Fu. Today I'm more happy to share our recent research in the development of new technology for cost-effective water production. So first, what I do, as you can see, my research covers three research fields. So namely, development of the radical polymerization technology, the development of new membrane materials for CO2 capture, as well for energy generation. And today I will talk this topic, the development of functional hydrogen materials for the solar vapor generation strategy. Okay, so first I will talk about the research motivation, sorry. So that is the water scarcity. So this term refers to a situation that under the situation where the water supply or water quality cannot meet all, or cannot fully meet all the by all the users and under the current arrangement. So indeed, So currently, about 7 million people, 700 million people in 23 countries, so suffer from water scarcity, and it is predicted that by 2025 this number will increase to 1.8 million. And by that time, 2/3 of the world population could live under this water stress conditions. So this situation highlights the development of the water production technology. But we know that since last century, since 1960s, the our membrane technology has become mature. Can produce a lot of desalinated water. However, the desalination plant requires huge investment, initial investment, and the operation will also costly and consume a lot of energy. So in addition to this, the disposal of a large amount of this kind of rainwater will also cause environmental problem. So therefore, researchers propose this technology, namely the direct solar vapor generation. This can be considered as a cost-effective alternative for water production. So briefly, as shown in this figure, you can see, so the researchers developed functional hydrogen materials and placed them on the surface of water. And the hydrogen materials generally consist two kinds of components. One is the photothermal materials, the other is the hydrogen matrix. Oops, sorry. And then we place these hydrogens on the surface of water and in a closed system under sunlight irradiation. The photothermal materials can efficiently convert solar irradiation to heat, facilitate vapor generation. And the generated vapor in this closed system will be efficiently condensed, and the distilled water can be collected for use for drink, for example. So therefore, heat management strategy, including developing new photothermal materials to improve the photothermal performance, and reduce the heat loss, as well as the water management strategy. For example, develop advanced hydrogen matrix to facilitate water transport, has been developed and has been considered as efficient strategy to improve the SVG performance. In addition, so we also need these hydrogens can effectively reject the salt. And if the hydrogen can also have some antimicrobial properties, will be fantastic, because this is good for the practical application. So accordingly, our research group focus on the development of heat management strategy. So we synthesize a series of photothermal materials including 1D nanoroots, 2D nanosheets, or 3D nanoparticles. Yeah, and we compare their performance in the terms of the geometry. So in this study, we investigate the influence of the geometry of these materials on the photothermal performance. So this study, the initial study was conducted by my student Casey. So by varying the molar ratio of the initial materials, so through the same hydrothermal process, we first successfully synthesized this metal oxide or semiconductor photothermal materials. One is the 3D magnesium oxide particle, the other is 1D conventional magnesium oxide and nanorods. Yeah, as you can see, under 10 minutes of solar irradiation, both of these materials can show very high photothermal performance. Yeah, so for the 1D photothermal materials, they can achieve 84 centigrade in 10 minutes. And then we incorporate these photothermal materials into the polymer hydrogels. This PVA polyvinyl alcohol solution, 10% mass loading, and introduce 1% of this photothermal materials. And I did cross-linker. Yeah, after cross-linking and frozen thaw, so we can successfully prepare two kinds of hydrogels containing different photothermal materials. And then we characterize the map or ICM, for example. Through the ICM image, we find that the 3D nanoparticle or 1D nanoroots were embedded in the hydrogel matrix clearly. Yeah, and both hydrogels have this microporous structure. Yeah, this structure will facilitate water transport within the hydrogel. We also characterize for FTR, as you can see, all the characteristics were observed, as well as using the UVs. Yeah, and you can see when we introduce black colored photothermal materials into the hydrogels can efficiently absorb the solar irradiation. Yeah, they usually show very broad solar absorption spectrum from 300 nanometer to 2500 nanometer. Yeah, and in contrast, this PVA pristine PVA samples, as you can see, almost have no solar irradiation. Yeah, above 400 nanometer. And then we use this homemade setup to test the solar vapor generation efficiency, or the water evaporation rate of our hydrogel materials. And the results are summarized in this table. Yeah, as you can see, the PVA hydrogels with 1D nanoroots show the highest SVG performance compared to all the semiconductor-based hydrogel systems. Yeah, they achieve about 3.1 kilogram, 2.8 kilograms square meter per hour, as well as with very high solar to vapor efficiency. And this performance is definitely better than the 3D nanoparticle one. Yeah. Oops. Okay, so in the next study, my student Stella synthesized 2D photothermal materials. Yeah. So we use the bulk crystalline porphyrin or bulk amorphous porphyrin as the raw materials, and through a normal cold bath assistant sonication technology, so we can successfully exfoliate these materials and obtain this crystalline porphyrin nanosheet or amorphous porphyrin nanosheet respectively. And then we wash these materials and disperse them in water and characterize them by ICM and as you can see, the crystalline porphyrin nanosheet is relatively smaller or have a higher aspect ratio. Yeah, the thickness is about 7 nanometers, while the diameter is about 300 nanometers. And in contrast, the amorphous porphyrin nanosheet have a thicker thickness that's about 20 to 30 nanometers, while the diameter is about 500 nanometers. So the crystalline porphyrin nanosheet have a higher aspect ratio. Yeah. We also test the photothermal materials of these materials. So under the same 10 minutes solar irradiation, so both of the materials achieve almost same photothermal performance. So achieving about 56 centigrade in 10 minutes. And then we use the same polyvinyl alcohol as a polymer matrix. Yeah, added very tiny amount. It can be trace amount, like 0.1 weight% or 0.05 weight% of 2D materials as the photothermal materials into the hydrogels. Yeah, and through the same cross-linking, freezing thaw process, so we successfully prepared the PVA hydrogels with 2D photothermal materials. Yeah, with different methods of the photothermal material. Yeah. Then we use the same setup to test the water evaporation rate. of these materials. As you can see, the hydrogels loading only 1 weight% of chlorine, sorry, still not 1 weight%, 0.1 weight% of chlorine porphyrin nanosheet. Show the best evaporation rate, achieving 4/4 kilogram per square meter per hour. Yeah, this result is very good, and we just submitted this study. Definitely, we compare this performance with all the PVA-based hydrogels. Yeah, as you can see, 4.0 kilogram per square meter per hour is a very, very high evaporation rate, and this is resulting higher than all the other study systems. Yeah. So at the same time, our research also focus on the water management strategy, and my student Shudi conducted this work. Yeah. So in this study, we use graphene oxide because graphene oxide is relatively cheaper, and so that's why. And we can buy 1 gram of them. Yeah. So that's why I should use this 2D-dimensional photosol materials instead of porphyrin nanosheet. And we use graphene only 0.1 weight% graphene oxide and photosol materials. And in her study, we use different polymer precursors, so including the PVA, polyvinyl alcohol, here or PEG as different polymer precursor to construct the hydrogen materials. And accordingly, we obtain these 3 composite hydrogen materials. Yeah. So we first characterize the morphology of these hydrogen materials, as you can see from the SEM image. Yeah, all the hydrogels have micropore structure. However, interestingly, we find that this P here and the PPEG composite hydrogels, the pore size is relatively larger, and all the pores are interconnected, as you can see from this image. Yeah. So this structure is expected to show higher or fast water transport. So what's the reason? Yeah. So this result can be attributed to the difference of the glass transition temperature between these raw materials. So specifically, the PVA does have a higher TG, yeah, that's about 50 centidegree. So therefore, and the frozen process that's conducted at -18 centidegree, the polymer chain, yeah, lack flexibility. So therefore, in the hydrogels, the growth of the water crystal was limited. So finally, we obtained a micropore structure with a lot of small pores. Yeah, that's the case of PVA hydrogels. However, in the case of P here or PPEG hydrogels, the TG of them is very low, so below -40 centidegree. So therefore, during the frozen process at -18 centidegree, the polymer chain still show high mobility. Yeah. So therefore, the crystalline, the water crystal in this hydrogel can grow larger and larger, not limited by the polymer chain. So therefore, finally, we will obtain very large pore size, yeah? And they are interconnected. And this structure, as I said, are expected to show high water transport, rapid water transport, and finally, eventually, facilitate water evaporation. Yeah. So we definitely characterize these hydrogels or FTF or FTR or UVBs. Yeah. You can see all the characteristics of the different hydrogels were observed. Yeah, and all the hydrogels show a broad solar absorption spectrum. Yeah. So then we test the water evaporation performance of all these hydrogels as expected. Yeah, the PVA hydrogels, PEG hydrogels with graphene oxide as the photosol materials show highest water evaporation rate. Yeah, they achieve 3.6 kilogram per square meter per hour. Yeah, and this value is definitely higher than the PVA one. Yeah, PVA is about PVA 10% here. That's about 2.8. Yeah. Kilogram per square meter per hour. Yeah, so it demonstrates that the rapid water transport definitely affect the SVG performance. Yeah, and this work conducted by 2022. So at that time, we find that 3.6, this value is the highest one compared to all the conventional and 2D hydrogen system. Yeah, but the last study we conducted in this year, and we break this record. Yeah. So definitely this hydrogel was we test the SVG performance of this hydrogel against the seawater. Yeah. So as you can see in the cycle test, these PEG hydrogels can display stable SVD performance, even when you use seawater. The seawater was obtained from Harvard, Darling Harbour. Yeah, there's a real seawater from Sydney. Yeah, and all these materials show very stable performance. Yeah, that's around 3.6 or 3.7 kilogram per square meter per hour. Yeah, we also use ISP mice to test the ion concentration of the collected water. Yeah, as you can see, all the distilled water show a very, very low salt concentration. Yeah, and this definitely made the drinking water standard by WHO. So, this study here and the PEG, both of them show interconnected pores. Yeah, and the pore size is very big. But what's the difference between them, resulting different evaporation performance? I read this question to Shudi, to my student, and then we realized that maybe the polymer structure can somehow further affect the SVD performance, not from the perspective of physics, but from the perspective of chemistry. Yeah? So that's why we think this topic may be interesting. So in this study, I asked Shudi to prepare a series of hydrogens. Yeah, we use the same 0.1 weight % of graphite oxide and photochemical materials, all the same. Yeah, but we try different polymer precursors, as you can see, from the negative charge sulfuric acid group to the positive charge ammonia group with this kind of neutral ether group or hydroxy group. Yeah, use the same method, we crossing them and further sort them to prepare hydrogens. Yeah, as you can see, all the hydrogens have the micropore structure. Yeah. So interesting is that we find that for this hydrogen PN, yeah, this with the amine group as a pattern group, yeah, functional group, they show a higher intermediate water content. And these results are summarized in this figure. As you can see, PM hydrogens have the highest intermediate water content. And intermediate water is believed to at a slightly excited state. So that means the evaporative enthalpy of intermediate water is lower than the free water. So that means if we have a higher intermediate water content, so in this case it's about 78%. 78% of the water inside the hydrogen intermediate water are active by the polymers, by the hydrogen itself. Yeah, so therefore under solidization, it can generate fast water evaporate. Yeah, so firstly we use DIC to demonstrate this theory. So as you can see, through the DIC characterization, we definitely observe that the PEM show the highest equivalent water evaporation enthalpy. So we know that at room temperature, the water evaporation enthalpy is as high as 2,240 kilojoules per gram. Yeah. However, in our case, we reduce this number to about 1,000 kilojoules. Yeah. So we definitely tested the evaporation performance as expected. This hydrogen show highest water evaporation because it had high content of intermediate water. Yeah. And then we definitely do this kind of second test against the seawater, and we definitely observe that the salt concentration is very low from the distilled water. Okay, like our last study, we developed a novel dual-layer hydrogen system. Yeah, the top layer is composed of PVA and graphite oxide, and bottom layer are made from this this polymer containing this positive charge ammonia group. We also added certain amount of PVA because PVA can enhance the compatibility between these two layers. Yeah, because different hydrogens have different swelling ratio. Yeah, we don't want these two layers just a break. Yeah. So we characterize for FTR and UVVs, and first we demonstrate that the dual layer configuration definitely can enhance the heat insulation. So we test the temperature of the interface and the bottled water and observe a higher temperature difference compared to conventional homogeneous stream. Yeah, and without definitely test the evaporation performance, it's okay, 3.1 kilogram per square meter per hour. But more important, these hydrogens show a high salt rejection ability. So we test the SVD performance against seawater from the Sydney Bay, and also concentrated seawater. Yeah, as you can see, in this case, the obtained this water definitely have a very low salt concentration. through the hydrogen system. Additionally, due to the introduction of this positive charge functional groups, our hydrogens also show good antimicrobial property. Remember that to achieve the same effect, we can kill 99.99% of the bacteria. To achieve the same effect, so conventional study usually introduce several nanoparticles or use the carbon quantum dots. But both of them are expensive. We only need to tune the structure of the polymers and achieve this ability. So finally, give a conclusion. So firstly, we investigate through our study. We found that the 2D materials, they have a high aspect ratio. So therefore, they have some advantage compared to 1D and 3D photothermal materials. Because we only need 1/10 of the weight to save on some money. And secondly, the cryogens also display the desired properties, like the large pore size and interconnected parts. Thirdly, we also investigate this hydrophilic group hydrogens can be ranked in terms of this SVD performance and follow. So this amine group shows best SVD performance, but this amino group shows lowest SVD performance, and we demonstrate that the chemical structure of the hydrogen can also affect SVD performance, not just a physical property. And finally, we developed this novel dual layer hydrogens and demonstrate that this dual layer have multi-function. It can enhance the heat insulation, can kill the bacteria, can show very high salt rejection effect. Okay, finally, give thanks to my group members. This study conducted by Shudi, Casey, and Stella, and also thanks to my collaborator from UTS, and thanks ARC, ATSE, and New South Wales Government, UTS for their fund support, and also give thanks to my industrial collaborator. Finally, thanks Sean, thanks Michael, thanks all the organizing committee members to organize this fantastic conference, and thanks all the audience, and I'm happy to answer your questions.
Interesting keynote presentation. We have time for one quick question. There we go. Yes.
Thank you for the great presentation. I'm not really familiar with too much with material science, but I got a question on this hydrogel. I see there's recently been a lot of applications of hydrogel in wastewater treatment, trying to encapsulate or immobilize bacteria. How do you think your hydrogel material can also perhaps do that? And also, do you have any comments on this application? Is it feasible?
As I mentioned, that the chemical structure of the hydrogen definitely determines a lot of things, play a significant role in different applications. In my application, I introduced this kind of positive charged groups, so therefore the hydrogen can kill the bacteria. So within 1 hour of incubation, they can kill 99% or the 99%. But if we change the chemical structure of this hydrogen, otherwise we use other materials, for example, PEG. Use the biocompatible materials, biodegradable materials, definitely can somehow increase the compatibility between the hydrogens and the microbiome or the tissue or the cells. So I heard a lot of study about tissue engineering. They just use hydrogen material, to grow the human, not human, to grow the cells, the animal cells, on that and do the experiment. So again, the structure determines the property and for different applications. Thank you.
All right, thank you. Well, we might now wrap up now because we're at time, but please join me in thanking Dr. Fu for that nice presentation. Gesture of appreciation. We have a little gift for you, so the front here and Okay, now now it's time to introduce our next speaker from RMIT and Melbourne, where I'm from too. So that's some local colleagues coming up to talk. Is Dr. Biplop Kumar Pramanik, who's going to give a talk on unveiling the resource within extracting rare earth elements from mine tailings. So, Biplop, the floor is yours.
Thank you, Michael. I think I'll not take much time. I'll go directly to the point. We know about rare earth element. I think this is one of the demanding element, and the primary source is getting down. So we started thinking about secondary or an alternative sources. So this work has conducted by my PhD student Shurunjit, and this project has funded by CSL, Warren and Noshara. They are from CSL. I think there are a number of secondary sources we have. For example, fly ash, seawater, the mining waste is one of them. So we collected, if we talk about the little bit about mine site, in Australia we have around 95,000 hard rock mine site in Australia all over. And around 90% of them are inactive. And there are a lot of mine sites have tailing facilities. And this tailing facility is one of the source of pollution as well. And sometimes we know that it takes $1 million for a site, rehabilitation or management. So, and we also found that the literature has suggested some of the TSF contain critical minerals and can potentially be recovered for economic and economical benefit. Even in some cases, some of the TSF have concentration of rare earth element compared to the primary deposit one. At the same time, because my talk is all about rare earth recovery from mining waste, but I want to talk in details what we have done for this project. At the same time, not all TSF contain critical minerals, so therefore all does not have the same environmental impact. So therefore, if we can have a database about all Australian mining, that would be good to understand which tailing has potential of TSF and potential of rare earth element. So this we collaborated with CSR, we got data from them and from different sources, and with visual inspection we developed the database. And this is kind of one of the first of its kind in Australia, like in terms of tailing storage facility database. And this database, if we talk about the summary of this TSF database, we found that around 13,000 active sites and 84 are inactive. And total of around 1,100 TSF are identified with, only that we have only the TSF. As we said, that not all mining has the TSF facilities. And out of them, 103 TSF in Australia, they have the potential with rare earth element. So, and this is like a video tour of TSF database, how we develop using Google Earth. I think if we talk about one of the sites, for example, New South Wales, just if we go to the Google Earth and then it will show that what type of commodity we have in that mine site. Just will show it here. For example, is one of the sites in New South Wales. Maybe site 1, here the major commodity is gold, copper, zinc and lead. The similar way, maybe I'll show another active site in New South Wales. So it has a major commodity of gold. I think understanding this major commodity in tailing sample, then we can come up with, okay, can we really think about recovering some things from that specific mining, and what type of things we need to consider in terms of the recovery. Okay, then based on the database, we collected sample from 2 different mining in Australia from the tailing sample. One of them, I don't want to tell the name because this is still confidential, I think. This tailing sample has a high grade of rare earth, and one of the highest grade rare earth deposit in the world, we can say as well. And this is produced the rare earth concentrate. And when we have done some physiochemical characteristics, we understand that it has, the tailing is dry and has 13% of volatile organic materials. Another things we find out, because when we talk about recovery, so the particle size is very important, and 50% of the particle was less than 61.3 micron. So then we have done other characteristics like a geochemical characteristics, and the major mineral was goethite and the monazite, and the major element was iron. Iron was kind of considered as an impurity, and we want to consider the rare earth element recovery. If we talk about the rare earth one, I think that it is that there are two types of it. One is light, another one is heavy. This staining sample has light rare earth element, and we have a more concentration of cerium and lanthanum than the others. So, and we have done some different types of phase analysis and characterization and mineralogical characteristics as well. So as we said that most rare earth element grains are mined around by the iron, and if you look at these mineralogical characteristics, and because of fine grain, as we said, like less than 61 micron, more than 50% of the sample. So we thought maybe hydrometeorological route can be a good way to recover the rare earth element. And then we tried to listen with hydrochloric acid, and then we found that that is not effective and non-selective, because here somehow 89% of rare earth recovery, but 100% iron dissolution, and then we used sodium hydroxide followed by hydrochloric acid, and here the rare earth recovery was increased. Again, the iron was a problem, and then selective removal of impurities, particularly iron, was necessary. And then we tried to do some work on how we can separate iron from the rare earth recovery. From this sample, somehow in the main the treated sample, we have only rare earth from the iron. And the main then the next work was we tried to work with pH control and temperature control. And after doing that one at different pH and different temperature, and then you understand that almost 100% of particularly more than 97% of iron we are able to separate from the rare earth one. And here the sample, and here if we talk about the mass loss, because when you are separating iron from the sample, only 0.22% of rare earth lost, I think. So this is the work, and here in principle, I think we can say that iron impurity removal mechanism was almost pH dependent, and precipitate has around 96% of iron, and so that we can say that high rate of rare earth recovery was possible here. In principle, if we talk about the conclusion, and then rare earth recovered from iron-rich maintaining sample, and precipitate was around 97% of iron, and then means like rest of the sample was rare earth recovery. So our next target to work on how we can selectively recover each of the rare earth element that we have from the sample that we are currently working on. And this is the references, and thanks CSL and RMIT for funding the project.
Thank you very much. Thanks, Vibhor. Very, very important work, so thanks for the nice talk. Time for questions from the floor? Actually, you did very well with time, so you've got plenty of time for questions.
That's very quick, yeah.
Yeah, Andre.
Thanks, Vibhor. Very nice talk. I was wondering, clearly your study shows that, it holds great promise, right, for the recovery of the rare earth metals. So I was wondering, are there any particular, economical barriers or technological barriers to, scale up or maybe apply to a broader scale this process?
Look, I think, as we said, that we have been working with CSL, and we do have a lot of results, but we cannot show it yet.
Okay.
And we do have a plan. I think CSL and Linus, I think we are working with them for this work. I think there is a possibility of, we are thinking for the next stage, pilot scale of this one, because as I said that we have a number of results, and based on the results we're thinking about the next stage. And I think the way we found from our preliminary work and the lab as well, if we close to in the pilot scale, maybe they have a plan to utilize this concept to utilize in their mine site.
Okay.
Because they have 1 million ton of tailing sample, and managing them is an issue. At the same time, they really don't want to utilize the acid and other things. If something like alternative, that would be good. Maybe biolysing can be another option, but they are not really keen to go through that direction. Maybe can be a good one, but again, selective recovery and other things is an issue. Once they're there, maybe they think still, if we can come up with something acid leaching and other things would be good if you can reuse acid again and again, and our work is going to that direction.
Okay, thank you.
Yeah.
Thanks. Question?
Thank you, really interesting. I was wondering whether the work that you've done on the database, whether you've been able to or thought about connecting with others who are looking at alternative mine rehabilitation techniques that might be applicable for other mines. You've got a specific focus, but as you noted, it's quite a narrow pool that you're targeting. But the database itself feels like a really useful asset.
I think it's a good point, and I think we are planning to extend this database. For example, here we have only the major commodity. We don't know how much volume and what other things we have in the mine site, and this is still like a hard copy kind of. So we do have to extend this database with considering all these aspects and transfer to a web-based platform, and that would be a huge contribution, I think. And this is one of our work. I mean, the next work is discussing with the industry partner.
And just, so that's great, and just I guess one other thought on the back of it is the extent to which there's an opportunity to feed into government to
Yes.
help their
Yeah.
understanding around the nature of
Yes.
the challenge.
Yeah.
Because it feels, as you said, that didn't exist before.
Yes,
So
yes.
that's-
And we have been talking with Australian Geoscience to develop that one as well. I think we are in discussion with how we can make a bigger one. I think considering all these parameters we have, including the volume of different elements, and if we can transfer to the web-based platform, that would be a huge asset for, I think, overall Australia, so that everyone can go and see what is happening for the specific mines.
Great, thank you.
Yeah.
You're just following on from that. Does that database include like this certain elements in the estimated amount of those elements in each of those sites, so you kind of got an idea of how much potential is in the waste? For a company?
That we don't have exactly, but we do have some information from Australian Geoscience and maybe from CSL, because they have been working out there for a long time. So we can have some estimation. And those are based on the estimation, based on the dimension and other things, we can come up with close to that amount.
Yeah.
And maybe we are planning to, add those information to the next database.
Yeah, because I sort of wonder, these are very much sort of business driven.
Yes.
To sort of try to take the waste, it's like Andrea's question, what are the barriers? Like the mining site will just do what they can.
Yes.
They'll put the waste there because it's not profitable to take any more out of. So what's the incentive? If there's an incentive that says, okay, collectively, there's enough volume here to justify a business case to then go and extract it.
Yes.
That might help overcome
Yes,
the barriers. Yeah.
So I think Australian Geoscience and CSL, they have been talking on behalf of us, and they have the similar way of, like utilizing those and developing those kind of things, so that can help to them to think about, rather than taking as a problem, like if we can recover things, something, maybe from business point of view, they would like to do that one as well.
That's right. Yeah. If it's not driven by environmental reasons, by business reasons, that makes a huge
Yes,
difference.
and this is the plan.
Yeah.
Somehow we need to show, for example, only one mine site, they come up with, okay, how we can recover this one, and then if we can do that one, maybe they have the interest, definitely, but we need to come up with, as you said, the business point of view, how that is economically feasible for them.
That's right. Yeah. So the environment means as well.
Yes.
At the same time.
Yeah.
So do we have any more questions? Are we going? Alright. We could probably wrap up now. Is there another burning question? No? Okay. Please join me in thanking people for the nice talk and good luck with your work. Okay, so now we can move to our next speaker, Young Woo Chu, also going back to UTS again. It's good to see Young Woo. Who's going to talk on selective separation and recovery of rare earth elements using electrochemical methods. So, please, the floor is yours, sir.
Hi, good morning. My name is Young Woo. I'm a Chancellor Research Fellow in UTS. I'm very glad to see a lot of rare recovery talks this morning, including Dr. Kuplus, and following to my talk, there will be a Charles talk about the absorption of the rare earth elements. Today I'm going to talk about the selective separation and recovery of the rare earth elements. The title has been slightly changed. It's electric field-driven memory processes. So the rare earth elements, it's critical minerals for cutting-edge technologies, and usually is commonly defined as 17 heavy metal elements, including lanthanides, and they are called vitamins of industry because of their very unique physical and chemical properties.